There we go. So this guy is talking about finding the solution of the equation in the interval negative 2 pi to positive 2 pi. And then, of course, here we're talking about your tangent function will have a value of square root of 3. So I would actually say go ahead and, look at your unit circle, because obviously, unit circle gives us a lot of that information. So if you had to try and figure out where the tangent x function was equal to square root of 3, any ideas what our possible candidates might end up looking like? Now, again, if you look at it in terms of tangent of x being square root of 3, obviously you want to think of tangent of being, sine over cosine of x. So that's the ratio you are looking at. So how do you think the unit circle can help us with that? Because you have to think about, if it's sine over cosine, you are looking at y value on top of the x value when it comes to these coordinate. Okay, Katie, you've got pi over 3 or 4 pi over 3. So let's see, pi over 3 would be this guy over here. So if we're talking about pi over 3, you're taking the sine function, which is square root of 3 over 2, and then dividing it by the cosine function, which is 1/2. Abdul Aziz, okay? So if you're taking 3/2, square root of 3/2 divided by 1/2 at, your angle pi over 3, which in this case is x, square root of 3 over 2 divided by 1/2. You can also write it as square root of 3 over 2 times, invert that fraction on the bottom, so it becomes 2 over 1. So of course, your 2's cancel out, leaving us with square root of 3 over 1, which is perfect because that ends up giving you the answer square root of 3. So this angle will work. And then Katie, you also said 4 pi over 3. Is that what you had? Yeah, 4 pi over 3. So that's this angle over here. Now, if you actually just go in the counterclockwise direction of your unit circle, you do need the square root of 3 to be in the sine position or in the y coordinate. Now, if you look at this ordered pair over here, you will see this guy is a negative, but then this guy is a positive. So, positive and negative will give you a negative answer. So that's why this angle does not work, because we need a positive square root of 3, not a negative. This one over here, your square root of 3 is actually in the wrong location. It should be with the sine value, not the cosine value. So this angle does not work either. Same thing with this guy, wrong position. 4 pi over 3 is looking good. And the reason 4 pi over 3 will work is because both your x and y values are negative. So the two negatives will become positive. So that guy works. You have in 5 pi over 3, you have one negative, one positive. So this guy will not work either. 11 pi over 6, your square root of 3 is in the wrong position. So that doesn't work either. So yeah, you only have those two angles, but this is going from 0 to 2 pi. They are saying we can have an interval which is going from negative 2 pi to positive 2 pi. So how can we make those adjustments going on the negative side? So you also have 4 pi over 3. But now if you're going from 0 to negative 2 pi, which means, you are going in the clockwise direction, what do you think those angles would look like going in the clockwise direction? What is the measurement of 4 pi over 3 when you are going in the clockwise direction? Because remember, going in clockwise, 0 is of course our starting point, but then this guy is actually going to be negative pi over 6. This guy will be negative pi over 4. So, you know, everything changes direction. So how do you think that will change? The 4 pi over 3 going in the negative direction. Billy, very nice. Yeah, so it's actually going to be the negative of this angle. So it becomes negative 2 pi over 3. Very nice. So that will be negative. And then one more, because now we have to see how pi over 3, what will this angle become going in the clockwise direction? So what negative angle is that? Jack, very nice. Yes, perfect. It's going to be negative 5 pi over 3 because this one is actually going to be equivalent to this guy, but negative. So perfect, negative 5 pi over 3. So when you put your solution set, you know, you are going to say, these are all for the x values. There we go. So your x values, you're going to list all 4 of these angles. So 2 positives going from 0 to 2 pi, and then 2 negatives going from 0 to negative 2 pi. Alrighty, perfect. So that's going to be your answer for negative, for number 50, tangent of x equals square root of 3. I think I had another something here wrong one, sorry. Number 54, okay, let's take a look at that. So number 54, we are looking at secant of x equals 2. So remember secant, you know, of course, is going to be the reciprocal function for cosine. So when we're talking about secant of x being equal to 2, and let's go ahead and move this to our so secant of x equals 2. So remember, secant of x can be defined as 1 over cosine of x, right? So if you're saying secant of x equals 2, how will that translate into the 1 over cosine of x function? Because if secant of x equals 2, then that means 1 over cosine of x also equals 2. So if 1 over cosine of x equals 2, what is cosine of x? Abdul Aziz, very nice. Yes, because if 1 over cosine of x is equal to 2, then that means cosine is going to equal 1/2. So that's actually how you are making that relationship going from what they're asking you to find, but you know what information you can use. So set that equal to as 1 over cosine, which leads you to cosine being 1/2. And then, you know, of course, fall back on your unit circle and see where is your cosine function equal to 1/2 at, for which angles. So take a minute and list all the positive angles for 1, and then we'll come back and do all the negative angles. So let me see what you guys come up with. Any answers? Okay, let's see what you have. So I've got Abdulaziz and Katie. You guys have pi over 3 and 5 pi over 3. Okay. Let's see, pi over 3. Okay, so very nice. Cosine is the first coordinate, the x value. Alicia, Billy, okay, same answer from you guys. All right, very nice. So yeah, wherever your x coordinate in these ordered pairs is going to be 1/2, that's exactly where you know your cosine function is equal to 1/2. So very nice. We're looking for positive 1/2, so pi over 3. And then you guys had 5 pi over 3, which is this guy over here. And that's true because remember, that's where your cosine function is positive in the first and the fourth quadrant. So you will actually have nothing from the second and the third quadrant. So perfect. Now, what will these look like going in the negative direction? What will these angles become when you're going in the negative direction? So what do the rest of you think? I want to make sure everybody is comfortable, coming up with these. All right, so let's see, Jack, Abdulaziz, you're just making those angles negative because yeah, when you're going in the negative direction, the positive 5 pi over 3 actually ends up becoming negative pi over 3. So very nice, this angle will become negative. Come on, buddy. So negative pi over 3 for this guy, and then the positive pi over 3 actually ends up becoming negative 5 pi over 3 in the negative direction. Alrighty, perfect, very good. Okay, so let's go ahead and list all of these angles. So our solution set will be x equals, let's see, positive and positive 5 pi over 3, and then basically negatives for the same angles, since you are stuck in that first quadrant. Alrighty, perfect. So, a lot of these you will be able to use the unit circle like we just did with these two examples to help you, find those answers as long as you kind of, rearrange your equations and use sine and cosine to help you come up with those definitions. So this was what, 66 for our next example. And that's actually going to be right over here. And this is actually where we're getting into these damping functions. So I actually wanted to show you what those damp functions look like. And again, if you've looked through the video lectures, then you will have seen this. But basically, the idea is if you are, going to be multiplying your trigonometric function by, something in front of it, like an x squared, of course, it can keep changing. That's what we call as the damping factor. So what it does is it actually affects, of course, what your y values are going to be, but also affects the shape of your graph. Because if you think about this damping factor of x over here, that's basically, if you think about the line y equals x, because that's this line over here. So it's actually like an imaginary line. It doesn't actually show up, but what happens is you will see how it changes the shape of our graph over here, because now instead of having just a smooth sine curve like we've seen, it's restricted by this line y equals x, and then of course on the negative side you have that negative x. So now they kind of behave like asymptotes almost, but not quite definition wise, because this will now get blocked by this line, so it cannot go up anymore, and then it's going to go hit the line on the bottom. So it's always going to be restricted between kind of like those x lines, and that's what your function is going to end up looking like. You can kind of see in this example, we're multiplying our function by x squared. So you've got x squared of sine of 3x. So, of course, x squared is a parabola. So you will see it kind of now has this little parabolic shape, opening up and down. But then again, your sine function is kind of restricted between those lines. So that's kind of how this little damping factor works out to be. So you've got just those things to look at. And then I also wanted to show you, you have your basic graphs, kind of all of them listed in here. So your sine, cosine, tangent, cotangent, secant, cosecant. So you can kind of see how those general graphs look like. So just kind of bringing one of those concepts in here, I have number 66 that we are looking at. So it actually looks very similar to what you had in the example I just showed you. F of x equals x times sine of x. They're asking us to match the graph, with the function. And then they're also talking about describing the behavior as your x gets closer and closer to 0. So your graphs are labeled A, B, and C, D, and you have to choose which graph is going to go with number 66, x times sine of x. So let me try and bring those graphs in here. Not sure if I can make this any smaller, so I'm actually just going to make them bigger. Okay, so remember your function is x times sine of x, and they want to know, is it going to be graph A, graph B, graph C, or graph D? So if you had to choose one of these graphs, which one do you think would satisfy what the x times sine of x function would look like? A, B, C, or D? Because imagine what that line y equals x would look like and how that would restrict your graph for the sine function. Okay, Scotty, you are going with graph A. So that's this one over here. Okay, so Scotty is choosing this one. What about the rest of you? What graph would you go with? A, B, C, or D? Abdulaziz, you went with B. So that's this guy over here. Eusebia, you are also going with B. Alicia, Scotty, looks like you are in the minority when it comes to graph A. Katie, you are also going with B, okay? Aussie, B. All right, let's take a look. Let's clear this out. Let's see, Hero, you're also going with B. Okay, so B definitely looks tempting. What did I click on? There we go. B looks tempting because, when we're talking about this line, y equals x, because, they're talking about f of x being x times sine of x. If you think about that line, y equals x, it is a line that has a positive slope going up. So you can almost imagine that line, restricting this graph over here. So this guy is definitely looking very promising. Now, if you just move this to line, this line to graph A, you will see it's not quite restricting, especially on that left-hand side, because, we have this little bump which is going up here. So this is actually definitely not being, or at least not following that path for number 66 with that. So yeah, very nice, guys. Graph B is definitely going to be the graph you are matching with number 66. So, the odd number ones you can do on your own because it shows you the answers to that. Now, they were also asking you what kind of behavior your graph is doing as it approaches 0, as your, x value approaches 0. So what can we say about that? So as your x value is getting closer to 0, where is your y value going? Yeah, your y is also going to 0, right? Because think about this. As your x value is getting closer and closer to 0, your y value is also getting closer and closer to 0. So as x goes to 0, your function, or basically your y value, is also going to 0. So that's kind of what you're going to have for number 66 over here. Graph P, and then what kind of behavior your function is doing. So you will kind of see questions similar to this on your homework also, where they're going to have you matching, these functions that are being multiplied by that damping factor and how it changes the graph for your function. All right, guys, so that was the last part that I wanted to talk about from section 1.6. So again, most part of it is that graphing we saw last time. So just, again, make sure you are comfortable with that. If you have any questions, let me know. Now, we are getting into officially the sine inverse for our trigonometric functions. And these are actually the, the little, on your calculators, you see that sign with the -1 exponents on that. So sine with the negative, with the inverse symbol, cosine, tangent. So that's actually where we are getting into. Because if you remember when we had first introduced secant, cosecant, and cotangent, a lot of you had used that sine inverse as your calculation for calculating those. So I want you to understand the difference between reciprocal and inverse. Reciprocal, basically, you're inverting that, you're flipping it. But inverse means you are undoing what the original function does. So if you actually go back and think about the inverse functions we had talked about in college algebra, chapter 2 in college algebra. So for an addition function, the subtraction is the inverse, right? Because the subtraction will undo what the addition function does. In that same way, a square root will undo what a square function does. So that's actually what these inverse functions mean. So when we're talking about, the sine inverse function for the sine function, basically, if you look at this, they're talking about the one-to-one correspondence, which is very important when you're trying to find inverse functions. So you will see that same concept being used over here. We're talking about, you should have that one-to-one correspondence, which means your graph should pass the horizontal line test. Now, if I were going to draw a horizontal line through our sine function, it does not pass the horizontal line test because, your horizontal line is going to cross right over here, over here, over here. So it fails the horizontal line test because it should only cross at one point. So what we do is we restrict our domain. So if we say, okay, I'm going to restrict the domain of my function and I'm only going to look at what you see here in the black ink. So, if we only use this part of our graph going from negative pi halves to positive pi halves, if I restrict my graph within this interval, then yes, when I draw my horizontal line through this graph, it only crosses at one point. So I can find the inverse functions as long as I restrict my domain for these functions. So you will see we are saying for the interval negative pi halves to positive pi halves, of course, your sine function is increasing, so your values are going up. We are also saying on that same interval, your sine value takes on, the range of going from -1 to +1, because you can see at negative pi halves, our y value will be -1. At positive pi halves, our y value will be +1. So we are using, those two maximum minimum values on our sine function. And since it's passing the horizontal line test in that interval, we can say our sine function is 1 to 1. So that means with these restrictions on the domain, I can actually have an inverse sine function, and the inverse sine function, you can write it as arc sine, or you can use the inverse notation, which is, kind of looks like that exponent of -1. So arc sine or sine inverse are the same thing. It just depends on how you want to write it out. So we will actually use both notations just to make sure you get comfortable with both of them. But keep in mind that because we are restricting our domain, this is very, very important when you're working with these inverse trigonometric functions. So just kind of keep that in mind. So that means our arc sine value of x has to stay within -pi-halves to +pi-halves. And you can kind of see when we try to graph it, how this function ends up looking like. If you remember, so this is what your original function looks like here. And then this is what its inverse function looks like. If you will remember when we had talked about, and let me see if Desmos, let me put both of them together. With sine and cosine function or inverse functions, they are always reflections of each other with respect to the line y equals x. So if we think of this as our sine function, and here's our sine inverse function, and I'm actually also going to graph the line y equals x. So remember, our sine function has to be restricted. So that means since we're only going from -pi-halves to +pi-halves, all of this of your sine function is not there. So you're not looking at this part. And same thing on here, we're not looking at any of this part, because remember, you use the maximum value of +1 and the minimum value of -1 on that y-axis. So that is the sine function you are looking at. So if you look along this line, which is the green line, y equals x, you will see if I were to fold my graph along that y equals x line, the two halves would actually be overlapping on each other because they are reflections of each other. So that same property that we had seen in our algebra, algebraic functions, those same properties you will see here with these trigonometric functions also. And that's the reason why it's crucial for us to restrict the domain on our sine, cosine functions, because otherwise they are not going to be 1 to 1. So you actually see a lot of those same properties in these functions also. So one thing to keep in mind is going to be right here, your domain and range will switch from the sine to the sine inverse function. So remember, the domain for the sine function is going from -pi-halves to +pi-halves. So that actually ends up becoming the range for your arc sine or the sine inverse function. The range for the sine function goes from -1 to +1. So that actually ends up becoming the domain for your arc sine function. So those domain and range will end up switching places. Another thing I want you to pay attention to is this rewrite of how we are writing the arc sine and the sine function. So if I'm saying arc sine of x equals y, that is equivalent to if I were to say sine of y equals x. So if you actually think about this, what's happening here is when you have y equals arc sine of x, I am almost applying the sine function on both sides of my equation. So it's kind of like, if you were multiplying both sides of your equation by 2 or something like that. So what I'm doing is I am applying the sine function to both sides of my equation. And what happens is, in a way, you can think of that the sine and the arc sine being inverse functions are canceling each other out. So you're actually just left with x on the right-hand side and sine of y on the left-hand side. So that's kind of how we are defining this relationship between y equals arc sine of x and sine of y equals x. That's the easiest way that I can kind of explain to remember that relationship between the sine inverse and the sine function itself. So just some basic calculations that kind of showing you how to calculate some of these values for the inverse function. So if they're asking you to find arc sine of -1/2, if you again use this conversion to help you out, you will be able to come up with the value of what this function should equal to. So I've got a couple examples for us to work on here. Let's take a look at those. So I've got number 6. Let's go to section 1.7. Okay. Whoa. All right, so we're looking at number 6 there. Same thing, find the exact value of the expression if possible. So we're talking about arc sine of 0. So if we think about this as y equals arc sine of 0, if we had to rewrite this, this would be sine of y equals 0. And make sure you are staying within that domain and range. So for the arc sine function, remember our domain is going to be between -1 and +1, and the range is going to be between -π/2 and +π/2. So think about this, and again, you can use your unit circle. Where is your sine value equal to 0 at? Where is the sine value equal to 0? Abdulaziz, you're going with 0 in this case. Let me see if I can clear some of this stuff out. All right, Katie, you're also doing 0. Let's see, Alicia, you're also going with 0. Okay, so remember, since the range of your sine inverse function is -π/2 to +π/2 for our sine function, that means your domain has to be between -π/2 and +π/2, and the range has to be between -1 and 1. So that means you can only look on from this side to this side, because remember, on the negative side, this guy is -π/2, which means you can only look at these angles to help you come up with this solution. So yeah, very good. Only at angle 0 is your sine value equal to 0, because you can see with all of these ordered pairs, your sine is not equal to 0. So yeah, the only angle that satisfies this is going to be 0. So let's go back to our problem over here, and I'll get rid of this stuff in green. So this is telling us then the only y value that will satisfy this is going to be 0, which means this answer is also going to be 0. So arc sine of 0 is going to equal 0. Questions on this one? Okay, so why don't you guys try number 5? Let me see what you come up with. That is arc sine of 1/2. Let's see what you come up with that. Pi over 6, okay. pi over 6, pi over 6. Okay, so let's check this very quickly. I'm actually going to clear this out. Okay, very nice, guys. So again, when we're talking about arc sine, of course, that means we are saying sine of y has to equal 1/2. But remember, you are again restricted on the sine function to only look between negative pi and positive, negative pi halves and positive pi halves. So if we go to our unit circle, where is your sine function going to be positive 1/2? And that's going to be at this angle right over here, because your y value is 1/2. Or your sine coordinate. None of the other angles, because this guy doesn't work. This guy, obviously, this is negative. We don't need a negative. So none of these other y values are working. So yeah, you're only looking at pi over 6 for that. So yeah, perfect. So y equals pi over 6. So that will be the answer for this guy over here. And we should be able to confirm that looking at this. Okay, so while we are on the sine function, can you tell me for number 11, arc sine is 3? Arc sine of 3. Okay, and Abdul Aziz, do you have a reason why? Laurel, same thing. Do you know why? Yeah, let's go back to our unit circle over here. Oops. So if you look at this, now I'm actually going to go ahead and clear this out. If you look at this, your y values are only going from +1 to -1, right? All of these numbers here are in between +1 and -1. So when we say that your arc sine is at 3, which was this guy here. So when you're saying y equals arc sine of 3, you know, of course, that translates that sine of y has to be 3. But remember, the range for the sine function only goes from -1 to +1. So 3 is, of course, you know, outside of this range. So that's the reason why you will not find an answer. And they actually do want you to put in impossible as the answer choice. So yeah, some of these you will not be able to solve because it will either fall outside of your domain and range, as it were. So yeah, very nice. Okay, so you know, of course, you will have something similar when we're getting into our cosine function. So you can look at some more examples here in your handout. We're actually getting into graphing your arc sine function. So you can kind of see how, again, we use that relationship between arc sine and the sine function. And I guess my brain, just the way it works is I always just go ahead and create a table like I was creating it for the sine function. So I would keep my x values in the sine function going from -pi halves to +pi halves. Because remember, we have to restrict the domain of our sine function. So those x values for the sine function actually end up becoming the y values for your arc sine function. And then whatever the corresponding y values you would have for sine, they become the x values for cosine. So basically, if this was the sine function, you would have sine of x equals y. So these would actually be all your x values, and these would be your y values. But when you're looking at them as the arc sine function, For the arcsine function, you will see which was originally the y value on the sine becomes your x value on the arcsine, and what was the x value on the sine becomes the y value on the arcsine. So yeah, just create a table for your sine function and then switch your x and y values to create a table for the arcsine, or do this for any of arc cosine function, and you will be able to come up with your graph easily with that. So same thing's going to happen like you saw with the sine function. We will need to restrict our domain because the sine function starts at a maximum point instead of intercept. Our restriction for the domain is going to be between 0 and pi. So you can see we are going from 0 to pi on the x-axis. Again, you will see your maximum value is +1, minimum value is -1. So for your arcsine function, your domain is going to be restricted between -1 and +1, just like we saw with the arcsine function. You can see how arc, sine, and cosine will have the same domain values. However, the range for both functions is going to be different because for arcsine, your range goes from -pi-halves to +pi-halves. Arc cosine, that will go from 0 to pi just because of the way the functions start and end. For the tangent function, the arc tangent will be its inverse function. So this will actually have no restrictions. You're going from negative to positive infinity on the domain, but then your range is only going to be between -pi-halves and +pi-halves. So this is probably a table I would keep handy when you're working through your calculation. So that way, for your inverse functions, what your domain and range for each one of those is going to be. Because, anything that falls outside of this domain and range, you will not be able to use those x and y values. So it's kind of important to keep a track of these. So I've actually got a couple more examples for us to look through. Let's look at number 10, and number 10 is actually using arc tangent of 1. So same idea, if y equals arc tangent is equal to 1, then that means tangent of y equals 1. So now you have to think, again, you can fall back on your unit circle and think, for which angle do I get a tangent value of 1? Abdulaziz, pi/4. Okay, so let's take a look over here. So you can see wherever your x and y coordinates or sine and cosine functions are the same, you will get tangent of 1 because you're dividing square root of 2 over 2 by square root of 2 over 2. So yeah, pi/4. Now remember, the domain for the arc tangent function is -infinity to +infinity. So can we have more than one answer here? Or is it only going to be pi/4? By pi/4, because this is also giving you the same x and y values. So let's take a look at our question over here. Okay, so they're just saying find the exact expression if possible. Okay, so they're not restricting our domain. Yeah, so keep in mind, since your arc tangent is going to be -infinity to +infinity for the x value, technically that means this number 1 over here can be, anything from negative to +infinity. So that's the domain. But as the range goes, remember the range is going from -pi-halves to +pi-halves. So that will actually put a restriction on your y value, which means it will put a restriction on our y value over here. So since the y value in the tangent function can only go from negative pi halves to positive pi halves, that means you're only sticking with pi over 4. So even though this is an option that you have, but because we have a restriction on our range for the arc tangent function, you're only looking at pi over 4. So always make sure you are, like I was telling you, looking at those domain and range values to help you decide. So coming back over here, this angle is going to be, let's get rid of some of this extra stuff. Okay. So this y value is going to be pi over 4, and that's coming from that restriction on our range for the arc tangent function. Let's see, what else do I have for us here? Number 14. Okay, so this one is just changing a notation a little bit. Instead of arc cosine, we are using cosine inverse, but remember, this is the same thing as arc cosine of -2. So if you have y equals arc cosine of -2, remember that will translate as cosine of y equals -2. So what do you think you will have for this one? Number 14. And again, as you're looking at this, look at the domain and range restrictions for the arc cosine function also, because that will also help you guide through your answers. Arc cosine, your domain goes from -1 to +1, and your range goes from 0 to pi. Okay, so Billy, Abdulaziz, Jack, you are all going with impossible or undefined. So what's happening is with our cosine function, you are actually restricted with your x values between 0 and pi. So with your cosine function, you're actually going from 0 to pi. So you're only looking at these angles over here. So if you look at this, your y value for, the cosine value is restricted between +1 and -1. So this -2 actually falls outside the range of your, -1 to +1. So it's actually the same thing you had seen with that, what was it, number 11, I think, that we had done, with the arc sine function. So same thing, since it falls outside of the range for the cosine function, or it falls outside of the domain of the arc sine function, you will have no answer for this. And so that's why your answer is impossible, because you cannot find a y value which will satisfy an arc cosine of -2. So I've given you a couple different examples like this in your homework also. So hopefully you can kind of work through them using this idea. And, again, you have any questions, come and see me, let me know. And then, again, I would use those same strategies of creating the x and y table for your cosine function, and then invert the x and y values, and that will give you the table for the arc cosine function. You can do the same thing with your arc tangent function also, so you can kind of see what these inverse graphs end up looking like. Again, you've got your list of domain and range, if they have any kind of intercept, what kind of symmetry you are seeing. So you've got a nice little, summary underneath each one of these graphs. So that can also help you as you're looking through these examples. So this is kind of what we just worked on, evaluating these functions for arc, cosine, and arc tangent. If they're asking you to throw this into the calculator, then this is where you would use those inverse functions. I don't know if I picked any of the calculator examples or not. Looks like I might have number 24. We'll come back to the graphing example here in a minute. Let's take a look at these ones. So just to make sure you are comfortable, just plugging these in your calculator, let's see what you are coming up with for 24 here. Arc cosine of negative 0.7. And they're asking us to round this to 2 decimal places. Okay, let's see, Shu, you've got 45.57. Let me check. Cosine inverse negative 0.7. Yeah, I was gonna say that I did not get the 45 something that Shu had. Yeah, 2.3461. It keeps going and you're rounding it to 2 decimal places. So Shu, what do you think happened with your answer over here? And guys, you really should know at this point to keep your videos turned on. You should not have them turned off. Yeah, you still have to remember about the mode. It has to be in the radian mode because we don't know that this is a degree angle since you don't have the word degree or the degree symbol being used. So this is in radians. So make sure your calculator is in the right mode. So yeah, when you round it to 2 decimal places, you get 2.35. All righty, perfect. So that was 24. Okay, I had apparently picked other examples, but you know what? If you can do one, you can do the others. So 27, 32, looks like all of those are from that one. Okay, let's go back to this graphing example here. So this one here is talking about using a graphing utility. So, you can use graphing calculator, or if you are, comfortable with Desmos, then I use, honestly, I don't even know where my graphing calculator is anymore because I haven't used it in years. So I just fall back on Desmos to help me out. So they're basically saying graph the two functions, graph the line y equals x so that we can see, that they are reflections of each other in the same viewing window. And then, we can try and see if they are inverse functions or not. So let's take a look at the tangent and arc tangent function over here. So we'll just go to our Desmos calculator here. Clear all of this out. I'm going to leave the y equals x line. And then let's do our tangent function. So from functions, we can click on tangent of x. So you can see how our tangent function is, right? And we had, of course, seen this when we were graphing this by hand. Also, so your tangent function comes out to be, these repeating lines. And then let's do our arc tangent, which will be tangent inverse, and will be tangent inverse of x. So you can see, honestly, we just need this main line here. So honestly, we don't need any of these other curves from our tangent function. So this is, where we restrict our domain on the tangent function. And that's the reason why, with this tangent function, We are restricting our domain from negative pi halves to positive pi halves. So remember that will become the range of the arc tangent function. And then, of course, the range for the tangent function, this arm is going up to positive infinity. This arm is going down to negative infinity. So for the range for your tangent function is negative infinity to positive infinity. So if you go back and look at your handout, you will see those are exactly the values that we had switched for our domain and range on the arc tangent function. You will see how this range of negative infinity to positive infinity becomes the domain for that inverse function, and your domain of negative pi halves to positive pi halves becomes the range. And I just realized, yeah, these guys should be parentheses because you have asymptotes at negative pi halves and positive pi halves, so we can't include those. So yeah, those guys should be parentheses. So you can see that in your graph over here, or you can also see that in the domain and range for your arctangent function. So, if we don't restrict our domain and range, we will not be able to find these inverse functions. So just to kind of show you, what these graphs will end up looking like, you don't have to draw these by hand. Again, if they give you graphing in this section, it will again be choosing those 4 options, choosing one of them out of that. So I would still, make sure you have the right values, you have the right ordered pairs, and then use that to help you find the graph. All right, so these were calculator questions. So let's see, I think all of these are still the same. Okay, now we are actually talking about, how we can use composition. So again, if you need to refresh your memory, this was chapter 2 from our college algebra book. So anytime, the idea is anytime you do a composition, and remember composition means you're taking the answer of the inside function and then you put that into the outside function and you solve it that way. So, the idea is I would first simplify the f inverse function, whatever answer I get, I would plug that into my f function. And when you do this for inverse functions, your answer should always come out to be the same x value that you started out with. And that's how you know you are looking at inverse functions. So they're actually using that same property to actually help us solve some of these expressions. So the idea is as long as your x value stays between -1 and +1, your y value stays between negative pi halves and positive pi halves, and this is for the arc sine function. Then when you do a composition between sine and arc sine, whatever x value you started out with, that's the same x value you will end up with. For the arc cosine function, again, your x values have to stay between -1 and +1, but then your y value is going to be between 0 and pi. And that's, for the arc cosine function. So when you do cosine of arc cosine, same thing, x value that you start out with is the x value you end up with. You can switch that order of your functions with, taking the arc sine or arc cosine on the outside and sine or cosine on the inside. So in this case, it's the same thing. Whatever this y value you start out with for the inside function should be the final answer when you do the composition. Same thing over here with the arc cosine and cosine of y equals y. Now your domain and range are different for the arc tangent function. So domain is all real numbers. Remember, -infinity to +infinity for the x values. And then the y value is between negative pi halves and positive pi halves. One thing I want you to notice as the difference with this arc cosine function, we are including negative pi halves and positive pi halves in our y value because this is the arc sine function. But for the arc tangent function, you are not including your negative pi halves and positive pi halves, because remember, tangent has asymptotes at these two values, so you don't include them for the domain of the tangent function. That's why you're not including this for the range of the arc tangent function. And then you will, of course, notice those same properties over here. So we actually use this to help us simplify some of these expressions. So just make sure, as long as you're staying within that domain and range, you can be given something like arc tangent of -5 on the inside, tangent on the outside. So we're doing a composition. Now, as long as your -5 falls inside the domain of the arc tangent function, you will be able to simplify this. And we know the domain for the arc tangent is all real numbers. So -5 definitely works in that. So you are able to solve this and you get the answer as -5 using our rules of composition. However, if you look at this last example here, you have cosine of cosine inverse of pi. So the idea is, does the domain of cosine inverse have pi in it? Well, look at the domain for the cosine inverse function. It goes from -1 to +1. Pi is 3.14. So, obviously pi is a number greater than +1. So that means pi is not in the domain of our inverse function. So that's why you cannot find an answer for cosine inverse of pi. So, this is something a little bit new for us because we haven't had to do calculations based on domain and range, but that's going to have a big effect on these calculations. So just be careful when you make it to this section for homework that, keep those domain and range values handy, because you may think I can just apply this property no matter what your X and Y values are, but it's not going to be true. So we'll look at some examples for this next time on how to use this composition with our different functions. So we'll take a look at that next time. So again, guys, please work on your homework. You get stuck on anything, let me know. So have a wonderful day, guys. Be careful, and I will see you on Monday morning. So take care, everyone. Bye. Bye, guys. Be careful. Yeah, Scotty, sure. Alicia, did you have a question as well? No? Okay.